Da-da-da. And then there's a link somewhere. Who did I find it? Who showed me last time? Oh, here, this one. Link. Control C. Ooh, I'm getting better. All right. Exam 2. Live stream. And the link. Paste it. Insert link. Exam 2. To live stream. Now, exclamation point. So, and the screen is working. Oh yeah, you can read my email. Okay. All right. Hopefully nothing on there I don't like. Okay. Cool. Yeah. I can read. Okay. I can see. Okay, so what are we doing? We're doing let's do canvas. Okay, that guy. I think I already have it. Are you download the same guy? Chapter 2. Example for
Quick question.
exam 2 study guide. Here we go. Quick question.
You said that the final was cumulative, but it shows like chapters 15 and 16. You said the final was cumulative,
yeah,
but it shows 15 and 16.
Yeah, but then if you read at the beginning of the final exam review, it tells you how it's cumulative. There are questions taken from each of the first 3 exams. Okay, so here's our study guide, and we're going to try to go through here. And you are getting extra credit, so I'll pass around the attendance sheet right now. Start at the beginning. Start at the beginning. Okay. Starting at the beginning. What is a Kuiper Belt object? A Kuiper Belt object is found where? Where in the solar system would you find a Kuiper Belt object? By the way, this is exam 2 review. That's the second column, additional and back column only. Okay. I think it'd be okay. I mean, they're pretty fast. It's too many. Well, I have 2 hours. You should get enough time. But I know. Well, last time it was more. Let's just try. If we run out of, if it looks like we're running out of time, let's escape. Okay. So Kuiper Belt object is found outside of the orbit of which planet? Neptune. Outside of Neptune. It's also called a trans-Neptunian object. Exoplanet. What's an exoplanet? A planetary body found around another star. A dwarf planet. What's a dwarf planet? Actually, maybe we should stop and ask, what is a planet? Does anybody remember the 3 criteria by which a planet is a planet?
Revolves around the sun.
Revolves around the sun. Number 2. It is spherical because it has enough mass to pull itself into a spherical shape. That's number 2. Number 3, Pluto failed. What is it? It sweeps out the orbital path of any debris. Pluto doesn't do that. It goes through the Kuiper Belt, lots of stuff, right? Now, we actually looked at a video showing the asteroid belt has lots of stuff too, but we're not going to get into that. It seems like there's a lot of material that Pluto doesn't sweep out. So we call Pluto a Kuiper Belt object. You're doing it in this column, right? You can find your name. Okay. All right. What is the asteroid belt? Where do you find the asteroid belt? Number 1. Mostly, the main belt is found where? Between Mars and Jupiter, right? What is the asteroid belt? It's a bunch of objects. How many objects? Probably how many?
Over 1 million.
Probably millions, right? Maybe billions, as a matter of fact. And but there are, we've seen that they've tracked about 800,000, I think, 700, 800,000, a lot of objects. Okay, what is the Kuiper Belt? Where is, we just said that. Kuiper Belt object. Okay, what's the Kuiper Belt? A belt that's outside of the orbit of Neptune. It's a flat, planar belt, just like the asteroid belt is flat and planar. But now, outside of that, there's a donut shape, which is called the scattered disk, right? So that's outside of the Kuiper Belt. We've never actually seen anything from there, but we think, based on objects that are coming from that direction, that in fact there is this structure that's out there. And then beyond that is the shape of the Oort cloud. What is the shape of the Oort cloud? It's a sphere that goes around our solar system. A sphere, right? All right, so terrestrial planet. What are they? Name them in order from the sun. Mercury, Venus, Earth, Mars. There are 4 of them, right? What's special about a terrestrial planet?
They are the materials that they're made of.
Yeah.
No.
How are they different from the 4 that are on the outer part of the atmosphere, outer part of the solar system? They are solid, right? They're solid planets. They're Earth planets, right? They're made of mostly metal and silicates, rock, okay? All right, gas giant, what's a gas giant? Which planets are gas giants?
Saturn and Jupiter.
Saturn and Jupiter. Jupiter's out, okay? What makes them a gas giant? What are they mostly made of? Hydrogen and helium. Okay, do they have a solid surface? Do not have a solid surface. What about the ice giants? Who are they?
Neptune.
Uranus and Neptune, those two. Okay, what's special about them? Why are they called ice giants? Ice, right? What do they have that Jupiter and Saturn do not have? They have ice, lots of ice. They have an icy mantle. I didn't really go into that. But in the same way that Jupiter and Saturn have convection, they have convection in an icy mantle. An icy mantle. Okay? What's uncompressed density? What does that mean? Uncompressed density. You take the total mass divided by the total volume. The average density, okay. Just that's a stupid term. I don't even know why I have that in there.
Would that apply more to the gas giant? I mean,
Well, so which planets, the terrestrial or the giants, have higher densities? The terrestrial planets have higher densities, right? And then what happens is the gas giants have much smaller density. So maybe that's it. I don't think it's that important. Which one has the lowest density of all the planets in the solar system? Which planet has the lowest density? Average density. Saturn, right? It's less dense than liquid water. Okay, so let's see. What is a planetesimal? I know I didn't go over this very much. It comes to, anyway, anybody have an idea? It's a big chunk. Yeah, it's not quite a planet, but it's one of the big chunks that would eventually gather together to form a planet. What's an example? What would it look like? What does a planetesimal look like? Asteroid, right? Asteroid. Asteroids are planetesimals that never built a planet. So as a matter of fact, if you ask the question, what does a planetesimal look like? The answer is an asteroid. It looks like an asteroid. Exactly. Okay, what are the Trojan asteroids? What's special about Trojans?
they are the exact same degree in front of and behind.
What is that degree? 60 degrees. They orbit with the body. What does it do to? They orbit with the body 60 degrees in front of the object and 60 degrees behind on the same orbital path. So Jupiter has them, Earth has them, probably all of the planets have them, but we only know about Jupiter and the Earth right now. And there's something special about those points. What is it? The gravity of the sun and the planet somehow balance together and make that orbit possible and stable. So the next term is Lagrange points. Here's a bonus question. Does anybody remember the number of the Lagrange points that the Trojan asteroids would occupy? L4 and L5. They are the only two stable Lagrange points. Stable means that if you move a little bit away from the Lagrange point, you get pulled back into it. Unstable means you don't get pulled back, you get pulled away. Okay, it's not stable. That's a bonus point. How many Lagrange points are there? 5, okay. Why do you need to know the Lagrange points? Because there's a satellite that's going to be placed at one of those points. So I would like you to know the name of the satellite and which Lagrange point it will be located at. Who knows the name? James Webb Space Telescope. It's not launching now until 2020, but it's going to be the successor of the Hubble Space Telescope, the James Webb Space Telescope, JWST. And where will it be placed? Which Lagrange point? L2, which is actually beyond Earth, right? So it goes Sun, L1 is between the Sun and the Earth, and then L2 is beyond the Earth. L3 is on the other side of the Sun from the Earth. L4 and L5 are on 60 degrees above and in front and behind the Earth. Okay, Earth-crossing asteroids, what is that? An asteroid whose orbit crosses the orbital path of the Earth, and it could potentially involve the Earth somehow, maybe hit or orbit or something, right? Differentiation. Ooh, that's a good word. That's an important word. What does that word mean? Differentiation.
As do the planets, right?
With planets or big, larger bodies.
Spreading.
What does it mean?
Planets spreading out.
Not spreading out, no. Differentiating. Separating.
Separating.
Remember separating by how? How do you get layers in a planet? By density. Separating by density. So where does the most dense part go? Into the core, and then you get layers which are less dense. Which one is the least dense? The crust on the top, right? So that's differentiation. In order for differentiation to occur, what must be true about the body? It must be what?
Metal.
In the beginning.
Metal.
It must be molten. It must be molten. The whole thing must be, not solid, but it must be molten, able to move. Otherwise, you can't get the differentiation won't happen. Okay?
So that's the 4 terrestrial planets that can have this.
Yeah, that's right. The 5 steps of forming a terrestrial planet, right? We'll talk about it in a minute. What's a C-type asteroid? C stands for what? Carbonaceous, right? Is it the most common or least common asteroid? Most common. Okay, just make sure you know that. S-type, what's S stand for? Silicate or stony, right? And what is it most or least? It's middle, okay? And then the last type is M-type, which is metal. And is it the most or least common? Least common of the asteroids, okay? What is the snow line?
Beyond Jupiter.
Right? It's before Jupiter, 4.5 AU, it's just before Jupiter. What is it? Beyond that line, what can happen? Solid water ice can exist, right? Can crystallize out of the gases that make up the new solar system. The word albedo, what does albedo mean? Right? Reflectivity, actually, reflectivity. So we see it as brighter or dimmer because it reflects more or less light. But albedo means the ability to reflect light. So high albedo means it reflects a lot or not reflect a lot. High albedo means reflects a lot. What kinds of materials reflect a lot? Icy materials we've discovered. Ice reflects a lot. Dirty stuff, not so much, right? Okay, albedo, okay. Comet nucleus, what's that? That's the hard center of the comet. It's just solid pieces, right? What is a comet actually? What's the nickname for a comet?
Dirty snowball.
Dirty snowball, right? It starts off, it's mostly made of ice with a bunch of dirt. And then after it goes around the sun a bunch of times, what happens to all of the ice after a while? It sublimates away. And eventually what's left is just the dirt and maybe a little bit of ice still. But it stops acting like a comet because there's not enough ice to make a coma and a tail, right? So it'll just stop being a comet. It'll burn out, right? A comet will eventually burn out. All right, so what's the coma? What is the coma? How would you describe coma?
The atmosphere.
The atmosphere. Where does it come from? From the comet nucleus,
Some gases.
sublimating, right? And when does the comet have a coma? All the time? Okay, so let's try to use our astronomy terms. At what point in the comet orbit does it have a coma, and what point does it definitely not have a coma?
Perihelion.
Okay, when it gets closer to the sun, it has a coma. It heats up. So we call this the perihelion. So when it's near the sun, perihelion. And then what's the farthest point called? At aphelion, the comet doesn't have a coma, right? Where did the coma go? It deposits back onto the comet, right, for the next round. So it's still there. It hasn't left the comet. Okay. Now, any comet with a coma will have a tail, right? And what does the tail come from? Why does a comet have a tail? It's blowing in the solar wind, right? The solar wind is blowing, and the coma is like that, pieces of the coma that are getting blown away. But the comet actually has 2 distinct pieces for the tail. One of them is very straight. Which one is that? The ion tail. Why is it straight? Because what's blowing it is the solar wind, which is made up of charged particles. So charged particles interact more strongly with other charged particles. So the ion tail is really straight. The dust tail has a little curve to it. Okay, so if I show you a picture, hint, hint, you should be able to identify which one's which, right? Anyways, they both face away from the sun, but the ion tail is really straight away from the sun. Short period and long period comet. What's a short period comet? What does short mean? Less than 200. Less than 200 years. Where does it come from? Kuiper belt, right? Long period. What does that mean? More than 200. So less than 200 more. It's really weak though, because it could be like a million. Where did the long period comets come from? The Oort cloud, or maybe the scattered disk now, right? Now we have another place where they come from. They don't come from the Kuiper belt though. Kuiper belt is relatively short period. Outside that is where you get the long period comets, but it could be millions of years, right? Just keep that in mind. It could be really a long time. The Rosetta mission, right? What's special about that? Who sent it out there? Was it NASA? It was not NASA, it was ESA. What does ESA stand for? The European Space Agency. So I don't know that you have to know that, but you do need to know that it went to this comet, Churyumov-Gerasimenko, or 67P. I will probably write both names on the exam tomorrow. That's tomorrow, right? That's tomorrow, okay? So somewhere you'll see those names. I guarantee it, okay? So you say, what was the name of the mission that went to Churyumov-Gerasimenko? And it was called the Rosetta mission, right? Or 67P, I'll say that, right? And so you just have to recognize that. That's a pretty famous thing because we've learned more about comets from that mission than anybody else has taught us, okay? All right, so a bunch of words. Meteoroid.
In the atmosphere.
An object which has the potential to hit the atmosphere, has not yet hit the atmosphere. It's going to, or it could potentially hit. Okay? Meteor, what is that?
Is it the one that's burning?
It's in the process of passing through the atmosphere. Why is it glowing? What's glowing? A meteor. It's the air that's glowing, right? Make sure you have that clear. It's the air that's getting excited and glows from that energy that's being released by the hot comet, not comet, meteor. Okay, what's a meteorite?
It's already landed on.
A chunk that landed on the ground. You look it up, that's a meteorite now. A piece of a meteor that lands on the ground is called a meteorite. What's a bolide? Remember bolide? It blows up. So something that explodes. A meteor which explodes is called a bolide. Meteor shower. What's a meteor shower?
But meteors passing through the
Why?
atmosphere.
What's happening? Are they predictable or not? Remember? Predictable or not? Yeah, I have them on my calendar when they're going to happen. Every year they happen around the same time. They're predictable because what's happening? In a meteor shower, the Earth is passing through.
The Kuiper belt.
No,
the iceberg.
the trail of debris left behind by a comet. Okay, so we go through the same place every year. We get a little bit of a meteor shower. Okay, so when we pass through the debris left behind from a comet, we get a meteor shower. Totally predictable. Are meteors predictable in general? No, they're random. We don't know when they're going to hit. I mean, okay, it's starting to get better. We're actually making predictions. One was predicted a couple years ago, and it actually fell right when they said. So we're getting better at it, but still pretty random. Okay, we don't know when they're going to happen. Interstellar gas. What does that mean? Let's take the word apart. Is that like the Oort thing? Maybe even beyond that. The gas between the stars. The gas. That's what it means. The gas between the stars. Interstellar gas. Center of mass. What does that mean? Center of mass. Actually, should we go over like a quick example why that would be important?
Center of mass.
Center of mass. It's not hard, but there's two things that can be together: a star and another star, or a star and a planet. Probably more this time we did star with a planet, right? And so when a star and a planet orbit, they don't orbit one of the objects, they orbit their center of mass, okay? So there's two examples for center of mass. One of them, if the two objects are the same mass, right? They're both the same mass. Where is this object located? At its center. Where is this object located? At the center. Where is the center of mass of the two objects? What's the answer?
It's in the middle.
Right in the middle is the center of mass. Okay? But what's typical with a planet and a star is that the star is massive. It's really big. And the planet is kind of puny in comparison. And so the center of the planet is here, and the center of the star is here, but where is the center of mass located? Yeah, really close to the star, maybe even inside of the star, right, to be honest. I mean, where I actually, most of the time it's going to be actually inside of the star. So what does this mean? They will orbit this common center of mass. So what will the star do? It'll make a little orbit, and what will the planet do? It'll make a much larger orbit. Okay? So they orbit the same center of mass. Do you remember the orbital period? What must be true about the star and the planet? Do they have the same or different orbital periods? Your time taken to go once around? No, it does not. Do they have the same or different? Which one? Different. They have the same orbital period. They dance together. They must stay together. The same orbital period. Do they travel the same speed? No. Not even close. Right? I think that's what you're thinking about, right? Which one goes faster? The little one or the big one goes faster? The big one. The little one has to go around a big circle. The big one only goes around a little circle in the same amount of time. So the little one has to travel a lot faster. So which one goes faster? The smaller mass has to move faster around its orbit. Okay, everybody good? So what happens to a star when a planet is orbiting it? It just wobbles a little bit. And the amount of wobble tells us about the mass of the planet involved. Okay, so how do we see a star wobbling? How do we see a star wobbling? Remember, not the twinkle. I think you're getting close though. You look at the light. What happens to the light of the star? It shifts. That's right. Remember the radial velocity? Okay, it's called the Doppler effect. So when the star comes towards us, what happens to the light of the star? It is blue shifted. Yeah, it goes towards violet, right? It goes towards a higher frequency. And then when the star is moving away from us, it's red shifted. We can see that little tiny shift, and we can measure the velocity of the star towards us or away from us, right? So we can see that happening. We know that that star has a companion, a little planet going around it, all right? So that's the radial velocity method that we just described. Okay? When you use the Doppler effect to measure the velocity of a star, then that's called the radial velocity method. It only works if the star comes towards you or moves away from you. What happens if the star is just going across, like this, not towards you, not away from you? There's no Doppler effect. It doesn't change the frequency at all. So it only works when the star is coming towards us, blue shift, or away from us, red shift. That's the only time. Okay, what about the next one, the transit method? Oh, by the way, so remember that these three techniques. Actually, I didn't put direct imaging. It's really pretty bad. But what about radial velocity? Pretty good or not so good? It's pretty good, but it's not the best. What's the best method for detecting planets, exoplanets? Right, called the, what's the name? The transit method. The transit method has found thousands of new planets, 5,000 new planets, something like that. So how does it work? What happens with the transit method? The planet passes in front of the star. And what do? You watch I don't see the word up there, but you watch the light curve, right? The light curve. The light of the star dims a little bit, then comes back again. And so by measuring the dimming, you can figure out the size of the planet and also how far away from the star it is to make that kind of a. All right, Kepler Space Telescope. Why is that important? Which technique does the Kepler Space Telescope use to detect exoplanets? In case you didn't know. The transit method. Okay, it's super special because it has detected more than 5,000 new planets. That's what's cool about it. Right? What's a super Earth? A really good Earth, like
Body that orbits
something about it. Why did we say Earth?
other than the sun.
What would you say about its mass? Similar or different than the Earth? Bigger. A little bit more mass than the Earth, but not much bigger in size, right? It's similar. It's just a little bit bigger in mass than the Earth, but probably not much larger than the Earth. Yeah.
You know, Zena, like, you know, you say we send things out to different planets. and like all those aliens fighting with those other terrestrial or other beings sending stuff to our planet.
There you go. Maybe. No. We haven't been contacted yet. You'll know. You'll know when we get contacted. You'll be aware. Maybe you'll even get a message right in your brain. I mean, I don't know.
Or what if like as it's like descending onto a planet, it's about to
This is cool sci-fi, but not relevant. Okay. All right, what do we mean by the habitable zone? Goldilocks zone, remember it? Not too wet, just right. What is it? Not too hot, not too cold, just right. For what? What's the habitable zone based on? What do we want? Liquid water, H2O, liquid water, right? So it's just the right distance from the star to allow liquid water to be on the planet. And we think that that's a necessary ingredient for life. Okay? Yeah.
Liquid water as opposed to water ice, right?
Yes, we want liquid. We think liquid is kind of special. Now, here's a question. I know it's actually a little bit advanced, but we're going to be learning about it soon. Are all stars just like our sun? You know this, right? No, they're not all like our sun. In fact, you're going to be learning day after tomorrow, okay, that most of the stars are much cooler than our sun, smaller than our sun. You know what color they are because they're cooler. They're red, okay? They're cooler. So do you think, here's just a question. If the star is cooler, is the habitable zone going to be closer or further from that cooler star? Closer. It's going to be closer. You have to get closer to that cooler star to have the right temperature, right? Our sun, habitable zone, is where we are. We're actually in the right spot. What if the star was hotter than our sun? Where would we need to be? Even further away, right? So your habitable zone will change depending on the kind of star that you're around. Does that make sense? That's an idea that you should be aware of. Did everybody sign in? Somebody came in and got your extra credit. You can get it at some point, okay? Before you leave, okay? All right. Hot Jupiter. What's the hot Jupiter? You should be aware. Hot Jupiter is another one like Super Earth. Hot Jupiter. Hot Jupiter. Yeah.
Gas giant close to the sun.
There you go. A big mass star, a big mass planet, sorry, really close to its star. So what does it do? Does it make that star wiggle a little or a lot? A lot. It gives it a big wiggle, right? And that means it's easier for us to detect. So the radial velocity method is really good at finding hot Jupiters. Hot Jupiters meaning large mass planets, hot meaning close to the star, right? So hot Jupiters are the ones we find. Conservation of angular momentum. It's a pretty important topic for us. Let's go ahead and talk about like a solar system, right? When you take a solar system, right, which is a big, you know what it is?
Yeah, the spinning.
Yes.
When you go like this, it's slow.
Spinning slow at first. When you bring it in, when you collapse it, what happens? It spins faster. Okay, so this explains why solar systems, all the planets rotate in the same direction, or revolve, sorry, I just said rotate. They all revolve in the same direction around the star. Conservation of angular momentum, right? And why the rings of Saturn are so flat. Conservation of angular momentum. I didn't describe it for you, but it's going to be the explanation for a lot of things like that. Why all the moons orbit in the same direction for the most part, right? All the planets rotate in the same direction. That's conservation of angular momentum. What is the condensation theory? What does it refer to? Condensation theory. Where does all the stuff that forms the solar system come from? It comes from gas, right? That then collapses down to form the protostar. But in the leftover stuff, different kinds of dust forming at different distances from the star. What kind of dust grains, crystals form close to the star? Metal and metal oxide. A little bit further from the star, what kind of grains do you get?
Silicates.
The silicates, which are stony material. A little bit further,
Water ice.
we finally get water ice, and then we just did one more. A little bit further, you get the other exotic forms of ice: methane ice, ammonia ice, nitrogen ice, oxygen ice, etc., etc., etc. Ethane ice, blah, blah, blah. Alcohol ice. Okay. So the condensation theory says that you have to, very close to the star, the only things that will crystallize out of the gas are little pieces of metal and metal oxide. A little bit further out, you can get the metal oxide and also the silicates. A little bit further out, you get the metal, silicates, and the water. Further out, you get everything, right? Everything comes out of the gas. Okay? So depending on the temperature of the gas. Interstellar dust, protoplanetary disk. What's the protoplanetary disk? The disk of material that will one day form the solar system. It's around the protostar. Interstellar dust grain. I don't know. What's that? Interstellar, between the stars, dust. It's stuff that's left over after stars explode. It gets spewed out there into the cosmos. Core accretion model. What does this have to do with? Which kind of planet do we talk about? Gas giants. That's what this is talking about. Gas giants. How do you make a gas giant? First, you need what? A core. Once you've got the core of metal and stone, right? Then what? You start gathering the hydrogen and helium. So that's the core accretion model. Okay, wow, that's a lot of words. That is a lot of work. Okay, let's see. Be able to determine from the period of the comet where the comet probably originated. Short period comets come from Kuiper Belt. Long period comets come from the Oort clouds. Okay, identify the ion dust tail from an image. Okay, I mentioned it before. Now it's in your study guide. You need to be able to take a look at a picture, and what will you see, right? You'll see, let's draw this picture. Here we go. I'm going to show this. Let me try this. What does a picture look like, right? You'll see a comet. There's a comet. Can you guys see this? You can't see it. Okay, well, I'm going to draw one straight tail and then one curvy tail. Which one's which? This one is what? Ion. This one is dust. Okay, there. I show you pictures easy to see. Can you see that? Okay, it's easy. Okay. Easy to see that I love you. Okay, here we go. I don't know what that means. Hi, Mary. I wonder if my wife ever watches these. Probably not, right? She gets me live at home. Okay, number three. Here we go. Explain using the condensation theory how the different planets in our solar system came to large differing compositions. Why do they have different compositions? We kind of mentioned it already, right? The terrestrial planets have mostly what? Iron oxide, and then the silicate, right? That's it. You don't find a lot of water ice, not like the outer planets have. You don't find the other methane ice, ammonia ice, all those exotic ices. As you go further out, the planets can incorporate more and more things. So in the Kuiper Belt, what kind of materials would you find? Everything, right? Everything is found in the Kuiper Belt. We do have lots of ice as well, but we have everything, really. Okay? Is that enough? You want more? Don't go too deep. It's not that deep. Okay, so I'm okay with that if you're okay with that. Okay, conservation of angular momentum. What happens, we kind of already described it, right? As you collapse, what happens to your rotational speed? You rotate faster and you flatten into the shape of a disc, right? So it was a sphere. Okay, that's probably what I should have said, right? It started as a sphere, but as it rotates faster and faster, it stretches out and eventually forms a disc. Okay. Estimate the location of the center of mass. We kind of did that over there, right? For two masses, the same or different. Explain the activity of a comet on its elliptical orbit around the sun. We kind of did that as well. The sun is active when? Perihelion, or near the sun, right? It's not active when it's far away from the sun, at aphelion. Explain the heating and light that are seen when a meteor streaks through the atmosphere. So because I told you, I'm going to ask you to remember this. What is the most important reason for the heating of a meteor as it passes through the atmosphere? It's the air. What about the air? The compression of the air. It's called compressional heating. So it used to be that friction was the answer. That's not the right answer. That's just a little piece of it, it turns out. Friction is there, but more importantly, it's the compression of the air in front of the meteor that causes the air to heat up. Why do we get a streak of light? What's the light coming from? The meteor? No, from the air, from the atmosphere, right? Now, there are some times when you get light coming from the meteor itself. What's that called? Give me the name of something that's actually the meteor burning up. A fireball, right? A fireball is that meteor really burning up. You can see the fuel burning. That's the flames that the fireball have. Blah, 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 blah. Okay. How do M-type and S-type asteroids form? Anybody remember? This is something Phil told you a little bit about. What do they form from? A differentiated or undifferentiated object? They form from a larger object that was large enough to differentiate. It got a metal core and a silicate outside because of the differing densities. And then it smashed into somebody and broke apart. What was left behind were families of asteroids. I know you've heard about this. Hopefully you remember that. The families are the ones that come from the core will be M-type asteroids. The ones that come from the outer part will be S-type asteroids. You need to have differentiation to have M and S type. Which are the ones that are undifferentiated? Which there's a lot more of. C-type. The C-type never got together with anybody. They're still the same as they were pretty much at the beginning of our solar system. Okay. Blah, 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 blah. What are the different methods of exoplanet detection? Direct imaging, radial velocity, transit method. Which one is the best? Transit method. Which one's the worst? Direct imaging. Although it seems to be getting better, I'm really impressed. I showed you guys a Wikipedia, and they had like four planets showing up around that star. That's pretty cool. I didn't realize that. Ooh, I didn't tell you about this, did I? Ooh, shoot. Okay. I forgot about it. Oops. So there's a system that was discovered called TRAPPIST-1, right? And they discovered that there are 7 planets around the solar system that are in the habitable zone. So why would this be exciting? Can anybody give me a reason? Yeah.
There's 7 chances that there's life on.
Yeah, I mean, it just makes it more and more likely that we can find places that are really good for life that we could live on. If we could live there, then why couldn't something else live there? So yeah, that one, in past, I've actually gone into more detail. When this was first discovered, it was kind of more exciting. I probably could have taken it off. We didn't talk about it too much. So don't worry about that. I don't think there's a question on that, actually. Okay, where are the planets, the asteroid belt, the Kuiper belt? We've got this Oort cloud, right? They're in order right now. The planets, which planets come first?
Terrestrial.
Mercury, yeah, terrestrial, but not all of them, right? Oh yeah, all of them. Okay. Mercury, Venus, Earth, Mars. Then what? Asteroid belt. Then what? Jupiter, Saturn, Uranus, Neptune. The last 3 spell the word sun, right? Saturn, Uranus, Neptune. That's the right order. And then outside of Neptune, we have the Kuiper belt. And then after the Kuiper belt, we have scattered disk, which is like a donut shape called a torus. And then outside of that, the spherical Oort cloud. Okay. The Lagrange points, which I already mentioned to you. You want to draw them, or you remember? We just sketch them real quick, like you're supposed to just know. Okay. So which planet has Lagrange points? All of them, right? So it has to do with a planet and the sun. So you draw the planet, or you draw the sun. Here's the sun, and here's the planet. Here's the planet, right? The planet around the sun. Between the planet and the sun, there's a point called L1. On the other side of the planet, out here, is L2. You don't have to worry about exactly where they are, just kind of roughly. On the other side of the orbit from the planet is L3. Okay. I forget, I think leading is L4. I think this one's L4. And remember that the angle is what? 60 degrees. 60-degree angle. I think this is L4. I might be wrong. It could be L. I think that's right. And then this is also 60 degrees. And that's L5. Okay, those are the Lagrange points. And why are they there? What do the Lagrange points signify? Places where the gravity forces kind of work together to balance out somehow. Sometimes they work together, sometimes they work against each other. You are correct. Your Lagrange points are correct. Yeah, that's right. Yeah. 4 and 5. Okay, thank you. Okay, so all right, that's chapter 21. Yep. Okay, how do I get to the next page? What's the next one? Oh yeah, there we go. Oh my gosh, how many words? Okay. Don't be afraid. Just get it done. It's like, how do you get from one place to another? You take one step, and then you take another step, right? It's really far, it's like 100 miles, but remember that one? Every journey begins with a single step. Okay, what does radioactive decay mean? An element is blank, and so it radioactively decays. Unstable or radioactive, right? And so it will decay into something more stable. That's called the daughter particle. Okay, there's a concept called half-life, and you will have to answer a question about half-life. So what is the half-life? The time it takes for half of the material to undergo radioactive decay. So if I had, 16 kilograms of radioactive, carbon-14, okay, the half-life is like 6,000 years. Okay. How many years will it take before I have 4 kilograms of carbon-14? How many years? How many years will I only have 4 kilograms of carbon-14, and I'll have 12 kilograms of nitrogen-14, right? You don't lose the mass, it changes into something more stable. How many years will it be? 12,000 years. How can you tell us how you did that?
Because
what fraction is 4 of 16?
it is a fourth of it.
It's 1/4, right? And so what happens is each half-life is you multiply by a half. So 6,000 years, you multiply by a half. Another 6,000 years, and you do a half times a half. Another, right? Just every 6,000 years, you multiply whatever you have by a half. So half of a half is a quarter. And so the answer is 12,000 years. So 6,000 years, you have 8 kilograms. 6,000 more, or 12,000 years, you have 4 kilograms. 6,000 more, 18,000 years in all, you would have only 2 kilograms of carbon-14. Just cuts it down in half every time. Okay? So it's simple, but it's confusing at the same time. But anyways, that's the way it works. What is the core of the Earth? What do we mean by that? The central part. What's it made of? What elements? Iron and nickel, right? Are the two most important. Iron and nickel. The whole thing is solid, right? No, right? Which part is solid? The inner core, but the outer core is still molten, right? Still movable. What is the mantle? What is the mantle made of? Silicates mainly, right? Rocky material. And what's happening is the silicates are moving in this process called convection, right? And they actually push on the plates and make the plate tectonics work. What's the lithosphere? What's the lithosphere? That's where the mantle and the crust. Upper mantle and crust, which is solid. Okay, upper mantle and crust, which is solid. The crust, what is the crust? Is there just one kind of crust, right? There's 2 kinds of crust. What are they called? Continental crust and oceanic crust. What's the continental crust made of? They're all made of silicates, by the way. But they're high or lower. Lower density or higher density? Are the continents made of lower density or higher density? Lower. Lower density. What's the word that we use? It looks white in color. Granite. Granite. So remember the word granite. Granite, actually it's not just white, but anyway, it's less dense. What is the more dense stuff called that the oceanic crust is made of? Basalt, right? Okay, so basalts are dark in color, and they're made from what? What is basalt made from? How do you make it? From lava, from molten, from the mantle material, from lava, from molten stone. Okay? And it hardens into this dark rock that we call basalt. Okay, seismic waves, aka what? Yes. Earthquakes, right? These are earthquakes. There are 2 kinds, the S and the P. What does S stand for? Oh, what does P stand for? Sorry, P. Primary. Okay, S stands for secondary. So which one's faster? P waves are faster. They get there first. P waves are faster. Okay. What else do you know about P waves? They're a pressure wave. Can they travel through a solid? Yes. Can they travel through a liquid? Yes. Yes. P waves go through everything. What about S waves? Can they travel through a solid? Yes. Can they travel through a liquid? No. So S waves, what's the problem? When they try to go through the core, the molten core, they don't make it through. They get absorbed by the molten core. Okay, heat transfer, conduction, convection, radiation. I guess we talked about it earlier, I forgot. But anyway, those are the three ways that heat energy gets transferred. How does conduction work? They got to be in contact with each other. So the contact between the core and the mantle, the core gives heat to the mantle by what mechanism? Conduction. Right? The core gives heat to the mantle by conduction. The mantle carries the energy from the core to the surface, to the crust, by what method? Convection. The Earth radiates mostly infrared light in every direction, and that's actually giving up heat, causing the Earth to cool. What is that called? Radiation, right? So which process is happening in the Earth? All of them are happening, right? So you want to know which one is which and where is it happening, that kind of thing. What is a plume? All right, what's a plume? I don't know. So I don't think I talked about this. It's actually a movement of the mantle up, a plume of material. What happens when it hits the crust? It pushes on it one way or the other. It makes the continents move, the plates move, makes the plates move. Okay? What's a shield volcano? Hawaii. Or Mount Olympus is also a shield volcano. I forgot to tell you that.
Is that a pressure one?
What is it? No, shield doesn't mean fresh. What does it mean? How does it form? Layer after layer, it just builds up. Okay? So a shield volcano is kind of the typical volcano. There are other things that are not as typical, right? Plate tectonics, what do I mean by that? The movement of the plates, right? What do? They smash into each other or they move apart. That's pretty much it, okay? They come together or they move apart. Converge or diverge, that's actually the two basic categories. So what if two continental plates come together? We call that a continental collision. What happens when two continental crusts collide? What do you get? You get mountains forming, right? Where is that happening on Earth today? The Himalayas, right? The Himalaya mountains. Where did it happen in the past? The Appalachians. I think it's interesting for you to know that, right? It's happened before, many times before. Why don't the Appalachian mountains look so big anymore? They've been weathered away. They've been worn down by the weather, okay? Little by little, okay. All right, so what happens when continental crust hits oceanic crust? Who goes up, who goes down? Continental goes up, oceanic goes under, where it ends up cracking off right away. But, all right, we call it subduction. You get mountains there, but the mountains, instead of being made of the crust material, are made from the molten sandy material that is getting heated by the friction between the two plates. We didn't study that very much, but anyway, the Andes mountain chain is an example of that. The Andes mountain on the western side of South America is forming by subduction. Okay. What is a spreading center? What happens? Spreading center. The plates separate, and then what? The mantle comes up to fill the gap, right? So what happens when you have a spreading center? What do you get? Fresh oceanic crust. The newest crust in the world is found in the Mid-Atlantic Ridge, which is a spreading center. That's brand new crust, right? It's literally a couple hundred years old or less, right? It's fresh, maybe even today, right? What am I talking about? Could be today. Some new stuff today. What's a hot spot? And where do we see an example of a hot spot?
Yellowstone.
Yellowstone is an example. Another example. The Hawaiian Islands, okay? The Hawaiian Island chain is an example, right? Not just one island, a whole series of islands. What's a hot spot? A thin part of the crust where the volcano is going to form. And why do you get a chain of islands instead of just one? The plate is moving across the hot spot, you get a whole series of islands there. Okay, blah, 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 blah. Troposphere, stratosphere, mesosphere, ionosphere. Okay. So those are in correct order. Troposphere is the lowest layer. Stratosphere is the next layer up. Mesosphere is middle. Ionosphere. What do you have to know? What do you have to know? Troposphere is where what is? What's in the troposphere? Troposphere. That's where all the clouds are. All the water is in that bottom layer. So the weathering that we talk about is really based on the troposphere. That's where all the cloud layers are. We do have some stratospheric clouds too, but they're much less dense and not nearly as prevalent. Okay. So what's in the stratosphere? What do we find in the stratosphere? Something important. That's where the blank is located, which absorbs ultraviolet light. The ozone layer is in the stratosphere, right? The ozone layer is where the stratosphere is, the ozone layer. So that's kind of important, okay? Above that, we have the mesosphere, and something happening in the mesosphere, we think. That's where what happens? 50 to 75 miles up, what is that? That's where the streaks of light appear. Right? What streaks of light? The meteors are burning up in that layer. That's usually where they burn up, okay? So that's where the light show is coming from. And then above that, we have the ionosphere. Why is it called the ionosphere? So you have lots of ions, which are charged atoms. So it's very electrically active, lots of stuff going on. It also, by the way, I don't think I mentioned, does it reflect radio waves? It reflects radio waves. A really cool thing is you can talk to Europe by bouncing a radio wave from the ionosphere, the top of the ionosphere, or near, whatever the ionosphere. It can get all the way to Europe. Pretty cool. Right. Ozone, we know what that is. What's ozone? You know what it is? Dave, you want to know what it is? Do you know what it is? The chemical formula for ozone? Anybody know? What's it made of? O3, that's it. There's 3 oxygen atoms connected together. It makes ozone. That's cool. Greenhouse effect, kind of important. There's a bunch of details here. What is the greenhouse effect? How is it caused?
Carbon dioxide.
Now let's start with what is the greenhouse effect? Light comes through or not get through? Visible light, does it come through or not come through our atmosphere? It comes through. Gets absorbed by the earth, and then it tries to re-radiate in what form? Infrared. Does it get through the atmosphere? It gets blocked by the atmosphere. So what happens to the earth? It gets warm as a result of that. It is warmed by the light of the sun. That's called the greenhouse effect. Is it a good thing or a bad thing? It's kind of good. Remember, without the greenhouse effect, we would live on an ice cube. It would be really cold. I mean, not so cold we couldn't survive, but it wouldn't be very nice. No sunny days, right? There would be sunny days. There wouldn't be warm beach days, okay? You wouldn't go to the, well, maybe you would. You probably have thicker skin, maybe a lot of fur. We'd be very furry. This is not relevant, okay? So anyway, it turns out we like the greenhouse effect. What's the most important gas for the greenhouse effect?
CO2.
No. What is it? Who knows what it is? The most important. This one traps more of the heat energy than any other molecule.
Water.
H2O. Water in the atmosphere is actually the biggest contributor to greenhouse effect. So it's not the CO2. The CO2 is tiny. It's really small. But what are the other ones that you might be aware of? Besides CO2, there's one other that we need to know. We've been talking about it. It's more present on the outer planets. It's the reason that Uranus and Neptune are blue, and the answer is methane. Okay, methane.
Because of swamps, right? The swamps produce a lot of
The
methane.
swampy material, bacteria. This is the announcement. By the way, do you think that you should have to know about the new NASA announcement that came out last Thursday? What did they detect in the atmosphere of Mars?
Organic
Methane. And it changed. Did I tell you about that? I thought I told you. Yeah. It gets higher in the summer and lower in the winter, which is really interesting. It may be the first indirect evidence of life on Mars. Okay, I don't know that for sure, but I believe it. I actually believe that that's what it's showing us. Okay, we just haven't found the life yet. It's underground.
So life now or not?
Yes, right now, today, there's stuff alive on Mars. I'm telling you, that's what that says. Even though there could be other explanations, the simplest one is that there is organic life today on Mars, underground, where it's nice and safe and warm, and there's liquid water. Okay, I'm throwing my reputation out there. I don't care. I think it's right. I really believe it. Okay. All right. So greenhouse effect, what are the damaging compounds that we think we need to try to minimize the amounts of? The methane is a carbon dioxide. Okay, so methane, we do have a little, if we, it turns out animals use methane when they're living, and we could reduce our dependence on meat and cattle like that, and probably the world would be a little bit better. And then CO2 comes from what? Where do we get a lot of our CO2 from? Almost all of it, actually. Burning fossil fuels. Okay, so when you burn gasoline, the side effect is you put out carbon dioxide in the water. The water we don't care about, but carbon dioxide is the one that can cause extra heating of the earth. So the earth is getting hotter. Okay. All right, magnetosphere. What is that? Magnetosphere of the earth. Actually, but it's true for any planet, any object that has a magnetic field. It's the region where the magnetic field is significant. It's a region near a body where the magnetic field is significant. So what creates the magnetosphere of the earth? Why do we have one? Called the Dynamo Effect, right? We think that this is the reason we have a magnetic field. The circulation of charged particles, also known as electricity, circulating inside which part of the core? The molten outer core is creating a magnetic field. Okay? So without that, we wouldn't have a magnetic field. Solar wind, what's that? Solar wind. A common misconception is this the light. Is it the light from the sun? No. This is not light. That's something different. The solar wind, what is it made of? Particles. What kind of particles? Mostly charged particles, almost entirely charged particles. So what are they?
Helium,
Hydrogen, nuclei, which means a proton, a helium nucleus, which is 2 protons, 2 neutrons. You don't have to know that. But anyways, hydrogen nuclei, helium nuclei, and electron. That's most of what it is. Okay? Aurora borealis, aurora australis. What's aurora borealis? Northern aurora.
solar wind,
Northern lights.
the magnetic field.
What happens? The solar wind hits the blank and causes the auroras. Magnetic field, the magnetic field, right? The particles which are in the solar wind hit the magnetic field. They can't move straight. They have to spiral around. And then what happens? They give their energy to the air. They charge up the, not charge it up, but they give their energy to the air, which then glows, and the glow is mostly green. Okay. And what's aurora australis?
The same thing.
The southern lights. So northern lights, southern lights. Tides. What are tides? What's a tide? High tide, low tide. What is it? The ocean and the seas, right, get pulled in and out. Right. We get high tide. The water is higher on the beach. Low tide, the water is lower on the beach. Right. It's pulled towards us. Towards what? What is the main contributor to the tide? The moon. Right. The moon. Right. Okay. Yeah. Tidal wave. But which one is next in importance? The sun. So the moon and the sun are what give us the tides. They can work together or they can work against each other, right? So when they pull, so what is happening is the tidal force means what? When there's a, what is the tidal force? Anybody? The difference in the force of gravity acting on the near side and the far side of an object, which causes it to be stretched, right? It stretches the body out. This is why Io is volcanic, right? So the earth is stretched by the moon and by the sun. If they stretch together, we get what is called a spring tide. What phase of the moon is it when the moon and the sun are working together? A new moon or right? New moon and full moon give you spring tides. How many times per month do you get a spring tide? 2 times per month. It's a pretty common thing. Spring tide is not just in the spring, it's 2 times per month. New moon and full moon. How about a neap tide? What's happening there? So spring tide, sorry, what's spring tide? You get really big high tides and really low tides. There's a huge change in the tide, right? What's a neap tide? They're working against each other. So the sun and the moon are 90 degrees away from each other. So what does this mean? That you don't get a high tide, you get a low high tide, and you don't get much of a low tide, you get a high what did I say? You get a low high tide and a high low tide, which means that you almost get no change in tide, right? It's really tiny. Okay, so it's a weak tide. And when does that happen? First and third quarter. First and third quarter, 2 times a month. Again, right? You get these weak tides. So John Palmentary talks about it, but it's no big deal. If you pay attention to the phases of the moon, you know when you're going to get these particular tides.
Spring
So what
was
what phase? When they're working against each other. So the moon is 90 degrees to the sun. That's called first quarter, and 270 degrees. That's third quarter. So first and third quarter. All right. What's tidal locking mean? Tidal locking. Anybody tidal locking? There's an example of tidal locking. Can you give me an example of tidal locking? The moon. Our moon is tidally locked to the Earth. So what does that mean? Every time it goes around the Earth, it rotates at just the same rate. It's called the synchronous rotation, yeah? And so we only see one face of the moon, right? So it's tidally locked. The moon, by the way, listen, is tidally locked to the Earth. Is the Earth tidally locked to the moon? No, we're not. The moon is locked to us, but we're not locked to the moon yet, right? Remember what's happening to the moon and the Earth? What's happening to the Earth? Slowing down. Eventually, we will be locked onto the moon, okay? It's a long time, really long time. But we'll find out that there's some moons, Pluto, and the moon of Pluto, Charon, and they're tightly locked to each other. And that's a weird thing. We've never, actually, there's no other example that I can think of, right? But it does happen. Question?
I was just saying, which way are they rotating that it causes the tidal lock? Are they rotating in different rotations or?
Well, tidal lock has to do with the idea that the moon is not a homogeneous body. This is a little beyond our course anyway, but because of the inhomogeneity, it wants to be oriented one way towards us because of the forces of gravity. So tidal locking is something that didn't happen suddenly. It took some time. There's some kind of a mechanism by which the moon is able to slow down and then actually fit this perfect tidal locking position. Okay, so it's just, it has to do with gravity acting on a non-uniform body. It's beyond our course. Don't get too crazy on that. Yeah, it's something to think about. What is a crater? It's a pretty obvious question, but what is a crater? A hole in the ground, right? Formed when what happens? An impact happens. Somebody crashed into somebody else, right? What are craters a sign of? Old surface or young surface? Old, right? You have lots and lots of craters, that's an old surface. If there aren't very many, it's not as old. And if there's none, well, it's pretty fresh, right? So the age of a surface can be determined by the presence of craters or not. So there's lunar maria and there's lunar highlands. So the highlands and the lowlands. What's a maria? It's the flat, what color? Very dark, right? Black, they're very black. They look like oceans. That's why they were called mare or maria. They thought that they were actually oceans. That's the word for ocean. And so what kind of material are they? Basaltic. So I realize this is the next chapter. Do you remember what stage of planet formation is reflected in the lunar maria? Has a name. When the surface cracked and the magma came up through the cracks and filled the valleys, it's known as flooding. That's flooding, right? So when the flooding or the marias were forming, and they were filling in holes in the moon's surface. So what about the highlands? Do we see evidence of flooding there? No, no flooding, just lots and lots of what? Craters, lots and lots of craters. So which surface is very old and which surface is relatively young? The highlands are old. They're there, they've been there since the beginning, basically. And the maria were formed about how long ago? The late heavy bombardment, you're supposed to know roughly when it was. About 4 billion years ago, 3.8 billion, 4 billion years ago. Okay. Oh, it's right there, late heavy bombardment, okay. Late heavy bombardment was a period of time when everybody on the inner part of our solar system got hit by lots of debris. Probably because what? And this might be beyond your course, but let's say if anybody knows. What do you think happened to cause this bombardment? The two planets, yeah, Uranus and Neptune probably migrated a little bit further out, disturbing a bunch of the material that was in the Kuiper belt, forcing it to fly into the inner part of the sun. That's probably what happened. Okay, so a lot of stuff happened. Okay. The giant impact hypothesis refers to what? The formation of the moon. By the way, it's going to come up here in a second. Okay, but the giant impact hypothesis says that Theia was the name of the body. Theia, a Mars-sized object, smashed into the Earth, and then what? The debris splashed out into a big circle around the Earth that gradually gathered together and consolidated to form the moon. Now, why do we believe this rather than, say, the capture hypothesis? What's wrong with the capture hypothesis?
The material is found on the Earth.
Okay, something else, capture hypothesis.
The orbit's wrong.
The orbit, right? It turns out that the orbit of the moon is perfectly circular, and a capture cannot be circular. What's the shape of a capture orbit? Elliptical, right? So as soon as you see circle, it can't be captured. It's wrong. It just doesn't work. Got to be elliptical for that. Okay. So I'm going to get to the, let's go here. Determine the amount of radioactive substance. I did this a little bit in advance, right? After you have an initial amount, every half-life, it gets cut in half and changed into something more stable. Okay? Describe how plate tectonics, I kind of did this too, right? I think we went through all of them. Well, we didn't quite go through all of them. I didn't mention this one. Again, I don't think I have any questions, so maybe you want to ignore it. But what's happening in California is one plate is sliding against another plate. It's called the transform fault. I didn't put it in there, so I don't have any questions on that. I can tell you that, right? It's not on the study guide, it's not on the test. But that's why we have earthquakes in California, right? I should have it on there. I don't know why I don't, but I don't. So it's not on there, it's not on the test, okay? Not on there is not on the test, okay? I promise you. How do plate tectonics do that? Describe the structure of the Earth atmosphere. What are the layers called? I think we did this already, right? We good? Yeah, what's the bottom one? Where all the weather is? Troposphere, okay. And the next one? Stratosphere. The next one? Mesosphere. The top one? Ionosphere. Okay, got it? All right. I really don't want a lot. Don't go do it. It's not deep. It's very shallow, very shallow. How does the greenhouse effect work? Okay. And we know what's the most important chemical in the greenhouse gases? H2O. H2O is actually the most important. And where is it found? Which layer? The troposphere, right? That's the layer that absorbs infrared light the best, right? And the other ones do, but they're not as important. There's just not as much of them either. How does the magnetic field of the Earth function? How is it created? Where is it formed? What's the mechanism called? Describe how the magnetic field of the Earth functions. Okay, the Dynamo Effect, and that's the circulation of charged particles in the molten outer core. Okay, metallic stuff, right? Conducts electricity. And how does it protect us from the solar wind? The solar wind gets deflected, and the particles spiral around and give their energy up to the air, and that's the glow that we see. So we see it as auroras, right? The auroras are a sign of it. Compare the gravitational relative strength of the sun and the Earth on the moon. So which one has the largest gravitational force? A larger gravitational force? The sun or the moon? The sun pulls stronger on the Earth. Which one has the greater tidal force? The moon, right? So you want to just kind of remember that. That's important. Those are two different facts, right? The sun is just huge, so it pulls really strongly on the Earth. But the moon, being so much closer, has a larger tidal force, a larger effect on the tides. Explain why the capture and fission theory are not good. What's wrong? Okay, so we did capture already. What about fission? What should the fission be?
That it just kind of came out of the Earth.
Right, so the moon should be exactly like what part of the Earth? The inner part, the outer part, or the whole thing? Just like the outer layers. But in fact, the moon mimics the Earth. It has a core, has a mantle, has a crust. So it can't just be made from the crusty material or the mantle material. It's got to be somehow all of the material. So it's not fission. It doesn't work. Fission says that it was split off of the outer material of the Earth, and that would be mostly silicate, mostly mantle type material. Okay, so what is the accepted formation model now? Giant impact hypothesis. Okay, How do the features on the moon form, and how they tell us about the relative age? So how did the craters form? Stuff smashing into the moon, right? How did the mare form? Stuff smashed into the moon and cracked open the moon, and the mantle material, which was hot, basaltic material, came up and filled the valleys that were there. So the mare were, once upon a time, the valleys of the moon, but they're not there anymore. Okay, and how does it tell us about the age? We already did all that. The order of the layers, I think we got, I forget the size, I don't care that much. The lunar rotation period and the revolution period are the same. Sidereal revolution period are the same, 27.3 days. So the moon goes once around the Earth in 27.3 days. It rotates once in 27.3 days. That's what it is. Okay, moving right along. Da-da-da. Is this helping you? Yes. You feel good? Yeah. Is everything making sense? You still have questions? Okay. I'm asking. All right. Let's see what happens. All right. Hopefully you're going to do very well. Chapter 7. Mercury, Venus, Mars. Okay. Differentiation. Let's see what that word means. I think we've already talked about it, but let's see. What does it mean?
Differentiation.
What do you need? A molten body separates by densities into layers. So the formation of layers in a body of different density is called differentiation. It has to be a molten body. And which layer is the densest? Core. The core will always be the densest, and the crust will be the least dense. Okay, cooling. These are the steps. So actually, differentiation is that first gathering of the molten material splits into layers. Cooling. What happens during cooling? You form the crust. The crust is formed, right? You cool and you get a skin on the surface of the body. Magma flood, cratering. What's cratering? Getting bombarded by stuff. Okay, what's magma flooding or flooding?
It's when the mantle is covering up those craters.
Right. So the mantle comes up through the cracks that are formed, and after the cratering process, and then fills up the holes that were formed. And weathering is, what's weathering?
The tilt and axis.
And you kind of wear things down. What do you need in order to weather? You can't have this. You can't have, a planet doesn't have this. You won't have weather.
Tilt.
No, that's seasons. Atmosphere. You need an atmosphere. In order to have weathering, you need an atmosphere. Okay. So you can only find weathering on bodies that have atmosphere. Okay. What's a wrinkle ridge, or what's the other word? A lobate scarp. Should be lobate scarp too, but I think I left that out. It is a fold that's happening because what? So the crust is the skin of a planet. And what happens as the core shrinks is you have too much skin. And so the planet is collapsing underneath the skin, and the skin has to go somewhere, so it kind of folds up. And it makes these cliffs or little mountain chains or something. And those are called lobate scarps or wrinkle ridges. Where do we see that? Especially, it's found all over the place, but Mercury is the one that we talk about. And is Mercury still forming these? Today, Mercury is still forming these. So it's a tiny little bit alive, almost dead, but it's still cooling apparently because it's still forming new wrinkle ridges. Fossil magnetism. What's that?
Did we go over that?
With the wrinkle ridge?
No, the fossil magnetism.
Yeah, we mentioned, somebody talked about it in class. It's the idea that when you have a spreading center, for example, and the basalt comes out, and the magma comes out and fills that, it aligns itself with the current magnetic field. But if you study that carefully, you find out the magnetic field has been changing, right, over time. And so we've discovered that the Earth's magnetic field actually flips every 20,000 years or so, but not regular. It's not like a clockwork process. So do you remember talking about that? Not really. Okay. So did you know that the Earth's magnetic field changes polarity from time to time? And the reason we know that is because of fossil magnetism. So we can find evidence within the basaltic layer that the Earth's magnetic field has flipped. It's not a big deal. Really don't get crazy on it. It's not important. Okay, tidal synchronization, right? So what does this mean? That the tidal forces cause bodies to begin to synchronize or resonate with each other. So Mercury is another example of where we see this, an orbital rotational resonance. Does anybody remember the orbital rotational resonance of Mercury? It goes how many times around the sun and how many rotations at the same amount of time? So 2 revolutions and 3 rotations take the same amount of time. So it has a 2 to 3 revolution rotation resonance, or orbital rotation resonance. So this is on its way to becoming tidally locked. Is Mercury tidally locked? Not yet, right? It's not locked yet. That would be 1-to-1, like the moon is. 1 orbit, 1 rotation, 1-to-1, right? So it's not quite there. Oh, that was the word I forgot about. That's the caldera. That's on Earth. Remember I told you the volcanoes that sink down after the magma subsides? That's called the caldera. Sorry about that. I forgot the word. Oh, what's retrograde rotation? Which planet does that? Retrograde rotation, only one.
Venus.
Venus, right? Venus, either we say it's flipped over 180 degrees or so, right? Flipped over, or it's rotating in the wrong direction. It's rotating in the wrong direction. So Earth rotates towards the east, but Venus rotates towards the west. Right? That's weird. Nobody else does that. Right? No other planet. Caldera would be on Earth, a volcano which sinks after the magma goes away. I wouldn't worry too much about that. I forgot it, so I don't think it's a big deal. What's a corona? Coronate. Where do you find that? Which planet?
Corona.
Venus. That's a Venus thing, right? And what happened is the magma came up, it broke open and made this big pancake, and then sunk down again. So it looks like a what? It looks like a crater, but it's not a crater. Right? It's more like a volcanic feature, right? But it's not a crater. It looks like a crater. How many craters on Venus? Nothing, right? What does it tell me? The surface of Venus is pretty new, and we don't know exactly how it works, but the surface of Venus, every once in a while, seems to get just resurfaced. And that could be flooding that's taking place, or we're not sure exactly how it works. But probably some kind of volcanic activity is resurfacing Venus from time to time. Olympus Mons, where do you find that? Mars, right? The largest volcano in the solar system. Okay, Valles Marineras. Well, that's how you spell it. Okay, Valles, the Mariner Valley, found where? Mars again. Those are the 2 big features, right? Blueberries, what are those? Little tiny crystals of hematite, iron oxide, and they can only form in the presence of liquid water. Where do we find them? On Mars. Okay. The Noachian period, what was that? Special. A time when Mars had liquid water, so it had an atmosphere, so it had what? Keeping the atmosphere in a magnetic field, right? Remember that Mars was still warm at this time. So it was about 4 billion years ago, right? 4 to 3.5, something like that. A while ago, a long time ago, but it was a time when life was good on Mars. And then, actually, we'll come back to that question. Amazonian period, what's that? That's the cold, dry times right now. That's the current period or current era of Mars, okay? So funny about that. Okay. Be able to describe some of the features of Mercury's surface, okay? And why NASA announced last year it is still alive. Okay, I think I told you already. What are some of the features? Does it have craters on it? Lots of craters. It looks a lot like the moon because it's got crater after crater. But it also has these funny little ridges, right? Those are the wrinkle ridges or low-base scarps. And that was NASA's announcement that it's still just a tiny little bit of life. Explain how Mercury can be seen to have a thin layer of hydrogen and helium, but not really an atmosphere. Where does the hydrogen and helium come from? The sun, the solar wind, right? And why is it there? It's only there for a little while. It's been trapped by what? What force is keeping it there? Gravity. Mercury has gravity, right? So it holds that little layer for a little while, but it's going to end up going away. It's not permanent. It's definitely not an atmosphere. Mercury does not have an atmosphere. When you take a picture of Mercury, is it a fuzzy picture or sharp? It is sharp. That's a clue. Remember how Titan was so fuzzy today? That's an atmosphere. The effect of the atmosphere makes it fuzzy. Okay? And describe away some of the differences and similarities between the terrestrial planets. What are some of the similarities? They're made of rock and metal. Okay, the core, mantle, crust. They all have that core, mantle, crust.
They're closer to the sun.
Okay, they're closer to the sun. They're mostly made of metal and silicate, right? Anything else? The same? Do they have evidence of volcanic activity? All of them have gone through some kind of volcanic activity at some point. Let's see, what's different? Do they all have atmospheres? No, Mercury doesn't. But Venus, Earth, and Mars do. Okay. If they were volcanic, what kind of atmosphere should they have? What should be in the atmosphere? What chemical compound? CO2, right? CO2 is one of the things that is emitted when volcanoes go off, along with some sulfur compounds, right? But the CO2 seems to be, it's called a primary atmosphere. All of the planets begin with CO2 in their atmosphere. Venus still has it, right? Remember why? We think Venus went through a runaway greenhouse effect. And so it's got permanent clouds you can never see in there. It's got nothing but CO2 in the atmosphere. It's really hot, right? How about Mercury? No atmosphere, sorry. How about Mars, is what I meant to say. Mars also has CO2 in the atmosphere. So it seems to be still there, just not very much of it. And the Earth, does the Earth have CO2 as the major component of the atmosphere? Not anymore. What's the difference? Where did it go? CO2. Where is the CO2 from Earth? Is it still here or did it leave? It's still here. Where is it? In the rocks, right? It got locked in the rocks by what? By living processes, by the plants and animals. They incorporated it, and then it turned into rock eventually. So we can still find the CO2 on Earth. It's just in the rock. Okay, and then I mentioned that's an interesting idea. Maybe people will be able to pull the CO2 out of the atmosphere and help make it better. Okay, so what happened? What was left behind when the CO2 got pulled out? The nitrogen and the oxygen were left behind. And actually the oxygen is a side effect of life as well. So Mars doesn't have, that would be something else to look for in Mars. If we could see oxygen too, that would be really interesting, right? I don't know, okay. How can Mars, describe why Mercury and Venus and Mars do not have strong magnetic field. Is it all the same reason? Yes, no, maybe. How about Mercury? Why does Mercury not have a magnetic field? Is it big or small? It's small. Did it cool off or is it still hot? It cooled off. And once the core cooled off, what happened?
Lost the magnetic.
No more magnetic field. No molten metal, no magnetic field. Okay. How about Venus? Venus doesn't have a magnetic field either. Is it cool? No. Venus is the same size as the Earth. It's still hot. And yet it still has a molten core. But what's the problem? It's rotating very slowly. 256 days for one rotation. It's really slow. Okay, so because there's no rotation, there's no dynamo effect. So for Venus, it's not that you don't have molten metal, it's you don't have a rotation. So the charges don't circulate, right? And Mars, what happened with Mars? It's too small again, right? So it cools off, okay? All right, let's see. Explain how, list the evidence which supports the idea that Mars was once a wet world. Do we have any evidence? Can you think of a few things? Anything?
Organic compound.
Oh, well, okay, that's brand new. Don't use that one. That's brand new. Okay. And that actually, we don't know that doesn't mean that it once was a wet world. We have other evidence for that. What evidence do we have that supports the idea that Mars was once wet?
Is it because of CO2?
Not the CO2, no. That would be fine. What's wet do? How about the hematite, right? The little blueberries that can only form in a liquid water environment. How about the layers of rock called sedimentary rock, right? Those form when weathering erosion takes place, and layer after layer over millions of years forms rock, right? Sedimentary rock. And then is the water on Mars still there? It is. Where is it? It's locked in solid at the poles, right? Big, thick layers of ice. All right. So how did oh yeah, that's the end. Okay. How did Mars have the largest solar volcano in the solar system? What's the reason? What formed it? It's a shield volcano, right? What formed it? A hot spot. Okay, there was a hot spot. And then what? It grew. Did it grow a whole chain of volcanoes? Just one. So did the plate move? No. No movement. Okay. And then how did it get to be so big and not sink into the ground? What can you say about Martian plates? If there's plates at all, right? There's no tectonic plate anywhere. I mean, there's no evidence of Himalaya mountains or anything like that either, right? So we don't think there was plate tectonics the same way there was on Earth. So what can you say about the plates? Thick or thin? Thick crust or thin crust? Thick crust, which allowed it to support this big giant volcano. So Earth couldn't even have such a big volcano. It would sink into the crust and wouldn't be that big anymore. Actually, we do see that a little bit on Mars too, but it's able to be the tallest one. Describe, how do we observe seasons on Mars? What happens in the seasons? Ice caps, right? Ice caps, yeah. In the winter or the summer, do you get an ice cap? That would be winter, right? And what's the ice made of? Don't say water, because that's not it. Ice. What is it? CO2. It's dry ice. It's taken out of the atmosphere. So in the cold winter, you get CO2 ice caps. In the warm summer, what happens to those CO2 ice caps? They go back into the atmosphere. They sublimate, go back into the atmosphere. Is everybody clear? That's kind of cool. It's actually something similar to comets, and we'll see more. Okay, more stuff like that. Blah, blah, blah. The sun sets on Mars. We looked at a picture today. I looked at my study guide. I'm like, I forgot to tell them about that. Okay, what color? Sunset on Mars. Blue, right? And the reason why, anybody remember the reason why? The particles in the atmosphere of Mars are big or small? Pretty big. They scatter the red light, but they don't scatter the blue light. So the blue light can make it through the atmosphere and we see the blue sunset. All right, so let's see real quickly. We already talked about that one. What are the order of events that led to Mars becoming a dry, nearly dead world? So what is the order of events? Anybody want to tell me? How do we begin telling this story? We're telling people who don't know about Mars yet. What are you going to start off with? What's the critical first event? It's a small body. I'll give you a hint. It cooled off. The core cooled off. And the metal turned to a solid, which meant what? Bye-bye. Magnetic field. So the core cooled and it lost its magnetic field. That's the first kind of thing that happened. Because it didn't have a magnetic field, what could now come through and energize the atmosphere, sweeping the atmosphere away? The solar wind. Because there was no magnetic field, the solar wind was free to come in and sweep away that atmosphere. So that's the second thing. And then because there's no atmosphere, what happens to the water that's been on the surface? It now evaporates. It can't exist as a liquid anymore. So only the solid water at the poles was able to stay. The liquid water was evaporated. So it ends up being colder because now that you don't have the water vapor in the air, you don't have what effect? The greenhouse effect is much smaller than before. So it's cold, no greenhouse effect. Dry because it's lost its water. Cold and dry world, right? Got it? Hopefully. And then that's it. Okay, 5 stages of evolution. Number 1, cooling. Everything gets together. Matter accumulates from far away. Lots of gravitational potential energy smashes together. Differentiation. Second stage, cooling. Third stage, cratering, smashed by all this external material. Fourth stage, flooding, which cracks open the crust and the mantle flows up and fills the valleys. Fifth stage, if you have an atmosphere, weathering. Okay, those are the 5 stages. Venus is funky, flipped over, rotating in the wrong direction. What's the tilt of Mars? 25 degrees. That's cute, right? What's the tilt of the Earth? 23.5. Pretty close. What's the rotation period of Mars? 24 hours and 37 minutes. I actually don't care that you know the exact number, but you should know that it's really close to the Earth. That's pretty cool. Like we could go there, and it wouldn't be a big difference. It would be a little difference for us. Okay. Okay, our last chapter. Are we gonna finish? Ooh, this is it. It's kind of shorter, isn't it? Can we finish? Yeah. So yeah, 20 minutes. Okay. What is okay? So I only mentioned this very, very briefly, but does anybody remember how the rings of Uranus were discovered? They block the light of some stars. That's called stellar occultation. So I just very barely mentioned that today. But it's just something kind of cool. That's how the rings of Uranus were discovered. So they block the light of a star. That's called an occultation event. And so it was just by accident they saw that happen. And that showed them that it was present, that the rings were present. So which of the four giants, the two gas giants, the two ice giants, have rings? All of the above. They all have rings. Which is the most visible? That's why it's called the Lord of the Rings. Saturn is the Lord of the Rings. It's got the beautiful, visible rings. Why are they so visible? Can you give me a scientific explanation or a more astronomy-themed explanation?
Because the material that's in the rings is made up of ice particles.
So it has a blank high albedo, right? Use that word albedo. That's cool. That's a good word. Okay, high albedo. Okay, metallic hydrogen, special. Where is it found and why is it there? Where do you find it? Metallic hydrogen.
The mantle of the gas giant.
What is it?
The mantle of the gas giant.
The mantle of a gas giant. So the two gas giants are?
Jupiter and Saturn.
Okay, why is it that Jupiter and Saturn have metallic hydrogen, but Uranus and Neptune do not? They don't have enough mass, right? So Uranus and Neptune are too small to be able to create the pressures needed to have metallic hydrogen. You've got to get the atoms super close together in order for them to act like a metal. It's pretty weird. It's really weird, actually. You and I have never touched metallic hydrogen. That would be crazy. You know what, though? They kind of believe that maybe if you could make it, it could stay that way as metal hydrogen. The hard part is just getting it that way. But what if we had, like, metallic hydrogen? That would be crazy. That would be weird. Anyway, I don't know. Whatever. Okay, it doesn't matter. What are belt and zone circulation evidence of? And which planets do you have them in? Which planets display belt and zone circulation most prominently? Jupiter and Saturn. Now, actually, Uranus and Neptune have them too. But anyway, not as prominent. So the answer is Jupiter and Saturn. Okay. And what kind of process is happening because of belt and zone circulation? Convection. Convection. And which one is which? Which one is the rising gases? The zones. And which one is falling gases? The belts. Which ones are lighter? The zones. Which ones are darker? The belts, right? Which ones with a thermal camera, infrared camera, look hotter? The belt, because you're looking deeper into the planet. I told you guys that little explanation. Okay. What is the great red spot?
Storm on Jupiter.
A giant storm, right? It's an enormous storm on Jupiter. And why is it still there after 400 plus years? Why? It's still getting energy. From where? From inside of Jupiter. Jupiter's releasing thermal energy, which feeds that storm and keeps it going. Also, the high velocity winds on Jupiter are probably contributing to it. They really go in different directions. We didn't get into that. Don't worry too much about that. What does an oblate sphere mean? Oh, wait, we jumped. Hang on a second. Something else. How many moons does Jupiter have? 69. Don't forget. Okay, 69. Okay. Currently. Okay. What are the four biggest moons of Jupiter called?
Ganymede, Callisto, Io, and Europa.
Okay, so in order of distance from Jupiter, Io, Europa, Ganymede, and Callisto, right? Io's closest. I think I have more questions on that too. Oh yeah, there we go. Right there. All right, so keep going. What is an oblate sphere? It's not a perfect sphere. What does it look like? It's flattened, right? And why is it flattened? Which planet are we talking about? Oblate sphere. Saturn. It has a really fast rotation rate. It's squished out a little bit. It's a little bit wider at the equator than it is at the pole. Okay. And Titan, what's Titan?
It's a moon
the largest moon of Saturn, right? And Cassini and the Huygens probe, tell me about that. Where did Cassini go? To Saturn, right? And lived there for how many years? 13 years, right? Before crashing into Saturn. And it dropped off the Huygens probe. Where did the Huygens probe go? You watched a little video. Onto the moon called Titan, okay? And it saw some pretty cool stuff. What about Enceladus? What's special about Enceladus? It's icy crust, icy oceans, and really cool geysers of water that are jetting so powerfully they leave the moon and go into orbit around Saturn. Little crystals of ice. Which ring does Enceladus's geysers create? E. The E ring. Enceladus starts with the letter E. So E ring also makes sense that way, right? What are shepherd moons? They were moons that kind of keep the
I would say that they're the moons that are on the rings that kind of keep the other material in their
They
orbit.
actually keep the rings going. They herd the ring. Yeah, don't worry too much about the better. Orbital resonance says that if a particle is in a particular ring, that certain rings can be disturbed if they're too close to the same body, and they'll actually get kicked out. So you don't get, so the particles like to be in their nice little ringlets, and will maintain that because of this resonance. What's that mean? Orbital resonance. It goes back to the story that it takes a certain amount of time to go once around that matches the period of something else, and so it kind of reinforces it somehow. What's the Roche limit? Okay, so why do you need to know about the Roche limit? Are the rings of Saturn new or very old? They're not new either. Sorry. So were they born with the planet? No, that's the question. They were formed after. They had to be formed after. And because of their ice, why would being made of ice tell you that they had to be formed after? Saturn and Jupiter are both radiating energy. And so the ice crystals should be what? Sublimated by this process. They couldn't last forever. They're going to be burned up by this energy coming out of Jupiter and Saturn. So we know that they're pretty recent. So the Roche limit is what? The distance at which
The radiation.
a body comes in, it's too close, it gets ripped apart by the tidal forces. Okay, so it's the distance at which tidal forces rip a body apart, rip a rubble body like an asteroid or a comet, Kuiper belt object. Okay. Saturn E ring, I mentioned already. The ring is fuzzy or sharp? Fuzzy. It's fuzzy. It's not sharp. It's a very fuzzy ring. And by the way, it's also not very pancake-like. It's more like a torus, but whatever. Miranda, I think, oh yeah, that's the only moon that I asked you to learn about. Uranus, what was special about it? It was ugly, right? Remember that the top half is different than the bottom half? We think that two moons smashed together and formed one. I don't know what else to tell you. It's pretty jagged. It has big cliffs. I could have talked more. I didn't talk about it. What's retrograde mean? Retrograde. Instead of going the same way that everybody else goes, it's going in the opposite direction. Is it born with the planet? If it's a retrograde orbit, is it born with the planet? It is not. It's something that came from somewhere else. It was a captured object. And so which object are we going to specifically mention? One of the moons of Neptune called Triton. It's special because it has a retrograde orbit. It is a captured KBO, Kuiper belt object. And what's special about it? Has something else that's special. Has geysers of liquid nitrogen that jet out. It's pretty crazy, pretty amazing. Okay. Describe how the intensity of sunlight changes at greater and greater distances from the sun. The further away you go, the weaker the sunlight will be, or the lower the intensity will be. And so if you go twice as far from the Earth as the Earth is, 2 AUs, what happens to the sunlight intensity? It's 1/4. If you go to Jupiter, that's 5 AUs from the sun. We had this as a question. What is the intensity of the sunlight? 1/25. You got to square the 5. Okay? If you go to Saturn's orbit, which is 10 AUs, it's 1/100, 10 squared. as much sunlight as the Earth gets, right? Okay, describe how Io is the most volcanic body in the solar system. What is the source of the energy that makes Io alive? Yes?
Volcanoes.
No, that's the evidence that it's alive. What is the source of the energy, the heat energy that makes it alive? Tidal heating, right? Tidal heating, the stretching from what? From orbiting close to which planet? Saturn. Jupiter, right? Io is Jupiter's closest moon. So Jupiter stretching Io inside and causing it to get hot. And that's how it has 300 volcanoes at any time. Okay, describe the ring structure. Why is it so special? Made of ice. But what's so special? It goes way out there, 80,000 miles in either direction, right? Super big structure. And how thin is it? Remember? 10 meters thick. Only as thick as this room is wide. It's something the size of a planet that's only as thick as this room. It's kind of amazing. It's really crazy. There's nothing like it, right? There's nothing like the rings of Saturn. They're really amazing. Why are they visible? The giant, okay, they're made of what? Ice. Have a high albedo. Describe why Titan is such a special moon. This is a very open-ended question. Why would you say it's special? Yes.
Is it because of the geysers and nitrogen, but also because it's a river?
Not Triton, you got confused. Titan. This is one of Saturn's, the big moon of Saturn.
It has an atmosphere.
It has an atmosphere. Okay, now, I actually went over this today, so let's remind you, or remind us. Why does Titan have an atmosphere? Because it's so big, right? Nope. Our moon is just about as big, doesn't have an atmosphere. What is the reason? It's so cold. Because Titan is so cold, the atmosphere molecules don't have a lot of kinetic energy and they don't escape. Okay? So that's what you want to be able to say. Well, what's special about it? Does it have mountains? Does Titan have mountains? Does it have lakes? Does it have rivers? Does it have weather? Yes, all of the above. What are the mountains made of? Water ice, right? That's the stone. The stuff that is acting like stone on Titan is water ice. What is the lakes and rivers made of? Organic hydrocarbons, organic compounds like ethane, methane, propane, butane, organic compounds. Okay. Why does Uranus have the most extreme seasons? It's tilted on its side. 90 degrees is an extreme tilt. So in an 84-year cycle, it goes around the sun. How long is each one of the seasons?
20 years.
21 years, right? 21 times 4. Okay, what is peculiar about the ice giant magnetic fields? What do you say?
It's offset from the.
Yeah, it doesn't line up with the axis. So it's not a simple thing. I don't even get it. I'm confused by that. I frankly am confused. So Saturn and Jupiter, nice. I get that. I'm happy with those. Earth, I like. Okay, it's all good. But they're weird. They're kind of strange flows. I don't even get it. That's weird. I already went this. What's unusual about Triton? Retrograde orbit. It's going the wrong direction. Okay, where did it come from? Okay. It's a Kuiper belt object. It has what kind of an orbit? Circular or elliptical? We didn't say, but it must be elliptical orbit. Okay, it must be. Compare and contrast the layers inside the giant world. So what's in the innermost layer for both of them? Either the gas giants or the ice giants. Probably a little core of iron and silicate, right? Probably there. And then remember that that's the core accretion model. Because it had that gravity, it could pull in the hydrogen and helium. So Saturn and Uranus, Saturn and Jupiter have a special form of hydrogen that comes next. What is that? A mantle made of metallic hydrogen. And outside is normal hydrogen and helium, right? Which is called molecular hydrogen. Regular, we say molecular. I don't know why we say that. This doesn't make sense. Whatever, normal molecules. Yeah, it's not molecules. I don't know what that's called. I don't get it. Just ignore that. I probably should go read up on that. But anyways, okay. How about the ice giants? What's special about the ice giants? Core, same thing. Metal, rock, right? Silicate. But then they have a mantle made of what? Ice, different kinds of ice. Lots of water ice, but also ammonia and methane. Okay, those are possible. And then what else? They have an outer atmosphere with a little bit of hydrogen, helium, and then methane. And what's special about the methane in the atmosphere of Uranus and Neptune? It absorbs what color light? Blue. Red. No, no, it absorbs the red but reflects the blue. That's why they're blue in color. Compared to drugs. Okay. The 4 gallon memorized. Okay, we're almost done. We finished. We finished. Okay, here we go. And then I can do the 5 questions with you. Okay. The 4 gallon moves, Io, Europa, Callisto, and oh, that's reversed. It should be Ganymede, Callisto. I don't know why I put it like that. Sorry. Rotation rates and relative sizes of the giants. So how big is Jupiter compared to the Earth? 11 times as big. How big is Saturn compared to the Earth? The body, not the range. 9 times the Earth. How big are Uranus and Neptune? 4 times the Earth. Okay. What's the rotation rate of the Jupiter? We say 10.5 hours. I'm not sure, something like that. But Saturn is like 9.5, really strong. Did we talk about Uranus and Neptune? They go pretty fast too, though. They're pretty fast. Anybody remember? I kind of forgot. It's not important. 17 hours, I think, is one of them.
Oh yeah, 17 hours.
I forgot some. I forgot you about orbital periods. Remember the orbital periods? How long does Jupiter take to go around once? About 12 years. Saturn? 30. Uranus? 84. And then Neptune? 170 something, right? A long time. 174 years or whatever, okay? So the further you get, the longer you can go around. Okay, thank you very much. See you tomorrow. We have a little time in the morning too. If you have questions in the morning, come at the beginning of class and ask me your questions, okay? That way you really feel confident. Okay, we're gonna go over the 5 questions that were given as well. I think we're in. Everybody signed it? Get your extra pressure. Okay, let's go ahead and take a look. Sam, now take some candy, grab some candy, or don't ask. Candy make coffee. All coffee?
Not just like espresso that has like more. Okay. Then never mind.
All right, here we go. The 5 questions that are going to be on the exam. Question number 1. How do earthquakes reveal that the outer core of the Earth is molten rather than solid? Okay, so which one of these answers makes sense? The outer core of the Earth is molten. Remember? You want me to just tell you? Or what'd you pick?
Well, they gave me the answer.
Oh, you already got the answers? Oh, they gave you the answers. Okay. So let's talk a little bit about it. What are the 2 kinds of earthquake waves? What are they called? S and P, or P and S. P means what? Primary, gets there first. Secondary, S, right? So the P waves are a kind of a pressure wave. They make the material vibrate along the direction that the wave is traveling. Can they travel through a liquid? They can. Can they travel through a solid? Sure, no problem. Shear waves are vibrating up and down as the wave is moving forward. So can they travel through a liquid? No, they don't work. So what happens is as soon as they try to get through a liquid, they just get absorbed and they don't make it past. So behind the molten part, there's a shadow where the S waves can't get to. And so because of that, we can figure out the size of the S region, or the S region, the S wave blocking region, right, which is the outer core. So that was actually how they did that. And you might remember from our discussion, how did we know that there were going to be earthquakes? How do we know? Do we normally know? We don't know. They were man-made, right? They were made by humans. They were the atomic bomb testing, right? That's actually how we knew that. Earth's magnetic field is created by which layer, by the way? That's created by the metallic stuff that's in the core, but not the inner core, which is solid, the molten outer core. And what it does is it runs around as the Earth is rotating. It makes a circulation pattern, which we call the dynamo effect, right? So the dynamo effect. So the answer is C, right? The electric currents. Now remember, the answers can be scrambled, so but you want to remember the answers, okay? An atomic nucleus that transforms from one element into another, it has undergone, and there's a bunch of words, but you want to remember that the right answer is radioactive decay. And radioactive means unstable. So that atom is not happy being the way it is. It wants to turn into something more stable. So it undergoes radioactive decay. Number 4, the asteroid belt. Is the debris field of the destroyed planet? No. There was no Death Star that blew up a planet and left behind this asteroid belt. It contains as much mass as Saturn. Well, that's wrong too. If you could somehow gather together all of the asteroids in the asteroid belt, you would get something smaller than our moon. Okay, it's just not that much material. So it consists of roughly spherical bodies? Not really. They're actually really funny looking, right? They're lumpy. They're weird looking. They're not spheres because they're not very massive. When they're spherical, that means they're pretty massive to shape themselves into the shape of a sphere. Some of them, there are a couple really big ones that are spheres, but most of them are small. Was kept from forming a planet by the gravitational disturbance of Jupiter. That's the right answer. So most of the asteroids in the asteroid belt are just leftover planetesimals that just never made planets. Right? Only the largest planetesimals made planets. And the final question, this is the one we talked about with the tides. Which of the following situation has the smallest change in tide or variation in the tide? So the high tide is low and the low tide is high, but it doesn't change very much. That is called a neap tide. But neap tide happens during the 3rd quarter and the 1st quarter moon. So I think the best answer is A, B, and C. And they're all possible. All right, those are the 5 questions. Thank you very much. Good luck on your exam. End stream. Now I get to go make the exams.